So you guys were starting to take notes, and then we started talking about this, and I got a little scared because you guys weren't answering the limit as x approaches 0. So we went ahead and reviewed the vertical asymptote at x equals 0, how from below I was approaching, or the function's approaching negative infinity, from above positive infinity as indicated by the branches. But the overall limit does not exist. But pause. What limit would equal 1/2 the horizontal asymptote? What limit would equal 1/2? Oh, come on. You guys can at least start the limit. Huh? You're going to say DNE doesn't equal 1/2? That's weird. Give me a limit problem. How do you start any limit problem? You don't need that one formula. Just any old limit. Okay, the limit as x approaches. Good. You guys could have all said that. You don't know how to fill it in, but you could have said the limit as x approaches infinity. Does that make sense? How does x approach infinity? So as x approaches infinity, what are the y's getting closer and closer and closer to? Oh, hey, guess what? Could you have just done that one, or is there another limit that you could have also said? Yeah. What about negative infinity? Now, you can't do both. Andrew, is a good question. You can't do both at the same time. Because aren't they two very different approaches? They're infinitely different, right? So they're two very different approaches. I have to make them two separate problems. But as x approaches negative infinity of that one, positive infinity of that one, the limit of both will equal 1/2. Anyway, so horizontal asymptotes were actually going to infinity, or to negative infinity, equaling a constant. Vertical asymptotes were going to a constant and equaling infinity. Anyway, we'll come back to that. We had way too much fun with the beginning of 12.4. Let's go grade 12.3, tangent line stuff. I forgot. It's actually in the notes. I think it's a little too small, yeah? All right. Let's zoom in. Okay, let's zoom in. Here we go. 12.3. Let's grade. Number 4, the limit of a difference quotient. Number 6, -1. Number 8, -2. Number 12, the slope of the tangent line equals 2. Slope of the tangent line equals 2. Now, kiddos, what the book is doing, it looks a little different than what we're doing, but that's okay. I'm preparing you for what I want you to be prepared for. Do you guys notice how the book is showing it really, really weird? What's the book starting with in all of these? What's M subscript SEC stand for? The secant slope. And the secant slope doesn't have a limit in it. The secant slope says, fine, whatever, 2 points. There you go. But I wouldn't have had you starting with the secant slope, even though that's good. I mean, it's good for you guys to realize that the difference quotient is the secant slope, and then to get the tangent line, take the limit as h approaches infinity. But what did I have you doing from the very, 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 very beginning? Not finding the secant. I had you finding the tangent. But I had you calling it f prime of x, right? And I had you writing the limit from the beginning. And if you started writing the limit, what should you have kept doing? Writing the limit, writing the limit, writing the limit. For how long? For the whole thing until no more limit. Because you plug in h is 0. And then for A and B and C, I'm just on number 20, but the same thing would have been true for 14. Same thing would have been true for number 12. So don't stress about the book saying M, the secant slope, and then doing the difference quotient, and then simplifying the difference quotient, and then taking the limit. We started at the very beginning saying, we know where we're going to the tangent lines. Let's go straight to the tangent slope. So let's do the limit right away. And keep doing the limit until we solve. So number 12 is 2. Number 14 is -1/4. Number 20, what I boxed is the derivative is f prime of x, but A and B said, hey, plug in the point. Hey, plug in the point. So on number 20, since you had to plug in 2 different points, it wouldn't have been a good idea to start specific right away with, like, say, x equals 0. Because if you had started specific right away, you would have ended up with only the slope at 0. Like in number 14, how they went ahead and plugged in the 4 right away. It was specific right away. They ended with 1 slope and 1 slope only. But if you start general and solve the general derivative for all the slopes of a curve, then you get this equation at the end that you can plug in x equals 0, or plug in x equals -1, or plug in whatever you want and get lots of different slopes. That's how the general can be really useful. Number 34, final answer, 2x minus 3. How many of you guys used our cool shortcut rule with bring down the power to check at least once? Oh, only Dean out of everybody? No, I don't believe that. One more time. How many of you guys use the cool power rule, popping down the power to check your answer at least once? To check or solve it from the beginning at least once. There we go. Make sure you know how to use the limits, though. Okay. Let's keep going. I think there's another page, yeah? I knew there had to be at least a couple. Number 40 had a complex fraction. How did they do this magical jump? Good. They multiplied top and bottom by the 2 denominators. Now, this one's messy, though. We already did this one before in section 12.2, but remember, you have to multiply by the x plus h minus 5 and the x minus 5. They are 2 very different things. What you do on top, you also do on bottom. And why this is so nice is when you distribute these 2, the first one cancels, the second one's left. As you distribute again, the second one cancels, the first one's left. The bottom just has all these guys. You can go ahead and distribute your negative. Don't kill a seal. The x's should cancel. The negative 5s should cancel, or I should say the 5s should cancel. You have a negative h over h, which will reduce to be -1. Ha-ha! Plug and chug. -1 over x minus 5 squared. Pause. If you used the power rule on number 40, even though it might have worked okay this time, it will not always work without considering something extra. So please be careful. You don't know as much as maybe you think you might. So it did work in this one if you had tried that cool nifty trick, the power rule. It could have worked this time, but my warning, it won't always work if you have a u to a power instead of just an x to a power. Just a warning. Something called the chain rule, something called killing bunnies, which is one of the ones up on the wall that you guys have not seen yet. Okay, number 56. Parallel, same slope. So we were supposed to figure out that the slope was -2 by subtracting y equals mx plus b. So then we were supposed to find the derivative, 2x, set it equal to -2, x equals -1, and then go ahead and make a tangent line. I think that was our last even. Do you guys have any questions on 12.3? Yeah. 45? Okay. Is anybody still grading 56? It took some time. Are we okay? All right, let's look at 45. All right, cool kids, help us out. Number 45 gives us the directions. Find the slope of the graph of f at the given point, aka find f prime of 1. Does that make sense? The slope of the tangent line, the slope of the graph is the same thing as f prime, and at the point I'm trying to find it at 1. Is that okay? For just rewording all of this? Okay. If I was trying to do number 45 with the limit definition, it's up to you guys. Do you want me to start specific, end with the answer, or start general and end by plugging in 1? Start general, okay. So I have f of x plus h, so I'll have x plus h cubed minus f of x plus h. Guys, help me with the formula. What comes after f of x plus h? Minus f of x, so I need to go ahead and then put the x cubed minus 2x all over h, good. Are you guys cool if I use a little Pascal's triangle? 1, 3, 3, 1? Because it's a cube. So I have 1x cubed plus 3x squared h plus 3x h squared plus h cubed, a little binomial theorem. Action minus 2x minus 2h minus x cubed plus 2x. Don't kill a seal. Yay! Yay! Who's left? All guys with h's. Factor out an h. You have 3x squared plus 3xh plus h squared minus 2 all over h. H's reduce. I plug in 0. I end up with 3x squared minus 2. And some of you are like, man, that power rule would have been nice. Bring down the 3. Subtract a power. Bring down the 1. Subtract a power. Yay, 3x squared minus 2. Anyway, I'm supposed to be plugging in. I only have an x. I'm only plugging in the x. X equals 1 for that point. So what is my f prime of 1? 3 minus 2. So I found the slope at the point. Remember when I was solving all of this, I was solving for f prime of x. So once I got the 3x squared minus 2, I just had to plug in 1. So 3 times 1 minus 2 is 1. That's A. B says find an equation of the tangent line. All right, Andrew. What kind of line do I use for tangent lines? Y minus y1 equals m. Does that make sense? Oh, sorry. Which general equation? Point slope. So then for point slope, just to make things easier, let's take a new picture. Okay, so we just figured out that f prime of 1 is 1. For letter B, y minus, oh, they gave me y, right? Equals m, sweet, just found it, x minus. If you're in calc and this is a long answer, you're like, yay. If you're trying to check it with the back of the book, you should probably add the negative 1 to the other side and distribute. So you'd have x minus 1 plus a negative 1. If you're trying to check it in the back of the book, it'd be x minus 2. And then part C says graph the function and the tangent line. So if all went well, hold on. There'd be a max and a min at plus or minus square root of 2/3, which would be a little bit less than 1. Then normal cubic. Maybe somewhere. Nope, hit the 0, 0. Something like that. And then at 1, negative 1. Oh, just kidding. I should have just done this, shouldn't I? That'd be x squared minus 2. Ugh, plus or minus root 2. Hit somewhere after 1. Okay, just kidding. All right. Should have analyzed it a bit more. So I have my plus or minus square root of 2/3. You guys wouldn't know that necessarily. I have my root 2 and my negative root 2, which are my zeros. Then I have a point at 1, negative 1. Shoop, shoop, shoop. If you guys graphed that guy, and if you graphed this guy, you should see this guy skimming right at the point 1, negative 1. Does that make sense, kind of? All right, any other questions? Odds or evens? Going once, going twice. Worst comes to worst, just keep on like drawing lots of lines and then hope that it looks good. All right, here we go. Should not have been the moral of the story, but we tried. All right, kiddos. Let's get back to section 12.4. Section 12.4, it's time to go to infinity. And we already kind of have gone to infinity a little bit. We already kind of have gone to infinity a little bit in the answers, right? In the answers to limits. We've said as you come from below a vertical asymptote or from above a vertical asymptote, the y's are going to be going to like a positive infinity or a negative infinity. Maybe they'll be in agreement, maybe they won't be in agreement. I don't know if this actually helps, but I used it today with regular pre-cal. When does a two-sided limit exist again? Going to the same place. And what's that snazzy math term? Approaching. When they're approaching the same place, right? When they're approaching the same place, we can say when they're in agreement. I use this for pre-cal, and they didn't fully get the whole idea of approaching in two cars. We haven't done that. That'll be Monday. But I was asking about, is there ever a time when a vote needs to be unanimous? Like usually it's just majority wins. Jury, yeah, that's what I was thinking, like a hung jury, right? When a vote needs to be unanimous. So you can think about it as for a limit, it has to be unanimous, meaning from either side it has to be an agreement. And if one person doesn't agree, if one side doesn't agree with the other, then the limit does not exist. So if that does help, something silly, I don't know. I've never used it before, but for some reason it popped into my head today. So the idea of trying to make it easier on pre-cal. It has to be unanimous, meaning both sides must agree. But anyway, coming back. So as we approach a vertical asymptote, we've had answers to limits be infinite before. If it skims going down, skims going up, but we haven't actually gone to infinity before. But wait a minute. Even though we haven't gone to infinity, haven't we talked about horizontal asymptotes? Reset table of contents. Find me where we talked about horizontal asymptotes this year. Go. Come on. Wasn't this semester, I can promise you that much. It was when we were talking about functions before trig. Chapter 3. Wasn't that trig? I think it was chapter 1.
1.6, library of
Like x squareds and like square and absolute value and like cubics and yeah. 1 over x. Which one? 1.6? 2.6. Go find 2.6. We've done horizontal asymptotes. How on earth can we do horizontal asymptotes if there are really limits to infinity? In chapter 2, we were doing limits. Yeah, I just didn't tell you we were. Or maybe I did and you had no clue. And you were just like, that's funny. So, how did we, if you do remember, awesome. If you don't remember, look at 2.6. How did we find horizontal asymptotes way back when before we ever talked about a limit? Nope. Did you look in your notes? Come on. How did you find horizontal asymptotes? 2.6. Testing. What tests? Degree tests. And Kevin was trying to keep reading and I interrupted him. Degree on top versus degree on bottom. And we asked ourselves, who wins? I knew someone would get there. Who wins? The top wins, the bottom wins, they tie. Guess what top wins, bottom wins, tie is a way of solving. Look up here, look up here, look up here. If horizontal asymptotes only exist, or when horizontal asymptotes exist, the limits to infinity exist, guess what we're going to use degree tests to help us find? Limits to infinity. So check it. Horizontal, oh guys, it was right there. Embarrassing. So, horizontal asymptotes, end behavior of a function. As x goes to infinity, what is f of x doing? As x goes to negative infinity, what is f of x doing? So this one is going to be not from the right, not from the left. This is going to be to the right. What is the function doing to the right? That's going to be our as x approaches positive infinity. And what am I going to say for x approaching negative infinity? To the left. So how the limit behaves, I mean, it's super, super similar. You're still approaching, but you're approaching in a way that you're never going to get infinitesimally close to or arbitrarily close to. No. You're just going to keep going. To the right, to the left. What is f of x doing? Now, end behavior of a function. Kiddos, do all graphs always have horizontal asymptotes? No. What are parabolas or quadratics doing as you go to the left or to the right? Right? They're ever going up. Well, or ever coming down, technically. They're ever increasing or ever decreasing. And you can be going down to negative infinity, up to positive infinity. All sorts of functions, polynomials especially, don't have horizontal asymptotes. What kinds of functions have horizontal asymptotes? What's the name of this type of function with the top and the bottom? Yeah, there's a snazzier name. Rational. Rational functions. So, horizontal asymptotes will only exist, limits to infinity will only exist if you have some sort of numerator versus denominator that you can do a shortcut degree test with. Moving on. Limits at infinity exist if the value of f of x. I have to change how a limit is defined just a little bit. You're still getting arbitrarily close. F of x is still getting arbitrarily close, but x is no longer getting closer and closer and closer to a constant. X is now increasing or decreasing without bound. And that's exactly what we just said as far as without bound is x approaching positive infinity, and x decreasing without bound is x approaching negative infinity. Same thing as our to the right versus to the left. And a quick note, as maybe you just saw, that a horizontal asymptote will exist at y equals L when the limit as x approaches infinity is L, or, doesn't have to be and, or the limit as x approaches negative infinity of f of x is L. Why am I making a difference between and or? What's the difference between those two words? If it was an and, I don't know if I would say agree, but they both need to be true. And or, only technically, one needs to be true. Algebraic approach. Even though the shortcut is the degree test, are the degree tests, which you guys already have written down in section 2.6 notes, and which we'll technically review in just a second. Even though the shortcut are the degree tests, there technically is another approach that any college professor would probably show you. So I'm going to show it to you too, so that they won't totally judge your high school, possibly, hopefully, calculus teacher when you might possibly, hopefully, take calculus or have some college refer to it, some college professor refer to it. They like to judge high school calculus teachers. It's all right. Well, they've kind of earned the rights, most of them. They've earned the right. But I have friends that teach at college that probably make way more and work way less, that teach way lower math. But that's okay. Their job is still important. And they earned the right. Limits at infinity. The book is going to say at infinity. It's kind of weird if you think about it. Limits at infinity? Why is that weird? Yeah, you can't get there. How are you supposed to get you're at infinity? Well, You're ever increasing, so you're at infinity? I don't know. I would say you're going towards infinity. So I say to infinity and beyond. But is there a beyond infinity? Where's n? N is just up there to say that x could be to any power. 1 over x squared, 1 over x cubed, 1 over x to the 1, 1 over x to the 1/2. N is just referring to any power, the nth power. Way back when, we actually looked at the graphs of 1 over x to the n, 1 over x squared, 1 over x cubed, 1 over x to the 4th. And they all had one thing in common. They all had a vertical asymptote at 0, and they all had a horizontal asymptote at 0. So at the very, very foundation of this whole approach is the understanding that the limit as x approaches infinity of any 1 over or even constant over x to a power will always be 0, whether you're headed to positive infinity or negative infinity. That's kind of the foundation of this whole process. And the step is to use this idea, to use this basic foundational, or these basic foundational pieces, multiply by 1 creatively using the 1 over x to the n, where n is the highest degree of x in any portion of the rational function. Now, the crazy thing about this example down below is we don't actually have to multiply by 1 creatively at all, because what we could do is we could rewrite this to be the limit as x goes to infinity of 4 squared. And what did I just say up above is true for any 1 over x to a power as you go to infinity or negative infinity. What's that guy headed to? Yeah. So the crazy thing is we can actually be like, oh, hey, since that's approaching 0, I can say this is the same thing as 4 minus 3 times 0, which just equals 4. This has to do somewhat with properties of limits and how we can take limits of piece by piece of one term minus the limit of the other term. So this one didn't actually need any sort of crazy manipulation of the function. We could just say, oh, hey, look, we see a 1 over. And technically, you could expand this just a little bit to say c over. It could be any constant. It doesn't have to be a 1. 2 over, 3 over, 5 over. We could say all of those are going to approach 0 as we go to infinity or negative infinity. But then things get a little bit more interesting. Now, I know there's this thing called a degree test. I know, but I want to show you the algebraic approach so that you don't look ignorant someday. So in order to find the horizontal asymptote, we're going to take the limit as x goes to infinity. Technically, we would need to check both the limit as x goes to infinity and the limit as x goes to negative infinity. But just for the sake of illustration, let me just go to positive infinity. There's only two times. Only 2 times where you'd have to actually check both to positive and negative infinity. Otherwise, there'll be an agreement. Ooh, 3 times. Struggle. 3 times. But whenever you have a normal polynomial over polynomial, it's nice, it's well behaved. What's going to happen as you go to the right will also happen as you go to the left. Anyway, long story short, it says, this process, this algebraic process says, check the numerator, check the denominator, find the term with the highest power of x. And guys, what's the highest power of x? And multiply top or bottom by 1 over x cubed. The process says, find the highest power. It's a cube. Multiply top and bottom by 1 over x cubed. Now, as you multiply top or bottom by 1 over x cubed, you would end up with the following. Let's see if this makes sense. 5 over x cubed minus x squared over x cubed reduces all over 1 over x cubed plus 5 over x squared when you reduce minus 3. Here's the crazy thing. Limits allow us to take it term by term, in the numerator term by term in the denominator. What did we say is going to happen to every single little piece where you have a constant or a number over x to a power? They're all going to approach 0. This is a clear way of seeing, oh, hey, all of those are going to approach 0. So it's not that we can actually cancel stuff out with our degree tests. It's that we're realizing as this expands, in the numerator, one thing is going to continually happen. It's going to continually approach 0 in relationship to the whole thing, and the bottom is going to approach negative 3. So what's our final limit? 0. How would our degree test get us to the exact same place? Who wins? Bottom. And what always happens when the bottom wins? The limit is, the horizontal asymptote is 0. And now we can say the limit as x goes to infinity is also 0. So where's this horizontal asymptote? At 0. So number 2, what are we going to multiply by? Close. Why did John put the question mark in there? And I totally agree with him because it was weird. Or it is weird. It's under a square root. So can I say just 1 over x squared? And here's the problem. No, I can't. But here's what I can say. I can multiply by 1 over the square root of x squared. What? I can't ignore the square root. He is a very important piece to this entire function. But I can say 1 over the square root of x squared, which does end up getting us to, since these both have square roots, I can actually bring that x squared in. And 4x squared over x squared is just 4. 1 over x squared is just 1 over x squared. But in the numerator, it starts to get a little funny. Because all of a sudden, I have 5x over, I guess I could make that the absolute value of x. But the struggle is, don't absolute values behave different ways based on whether you're working with positives or negatives? Maybe this is one of those special cases I was saying where you actually have to look both directions for what's going on. Now some of you might be pondering, hold on, there's a thing called a degree test. I wonder what the degree test would have to say with this guy. I wonder what the degree test would have to say with this guy. Guys, does someone go to 0 in here? He does, right? He's going to 0. So does that guy. I can say over 2, the square root of 4 plus 0. I can say over 2. Here's the dilemma. If I plug in positive infinity, yes, I know the degrees are tied, but pause. Isn't this going to be a positive over a positive? Positive stays the same, and a positive. Won't a positive over a positive be a positive 5? Pause. What happens when you plug in, oh, my negative. What happens when you plug in a negative, though? Isn't that a negative over a, ooh, and a negative over a positive is going to be a, can a function have 2 different horizontal asymptotes? Bye, cool kids. This homework is due on Tuesday, but I bet with your degree test going back to 2.6, you can do almost all of it. Bye, guys. Happy weekend. Happy Friday.